Good morning, everyone. Welcome to the GIST Sea Level Rise seminar. We're very glad to have Dr. Ryan Strickland with us today. He is a research fellow in the Department of Geography and Sustainable Development at the University of St. Andrews. And Dr. Strickland is broadly interested in feedbacks between glaciation, climate, and landscape evolution. He currently uses the 3D glacier flow model Elmer Ice to understand the dynamics of the eastern shear margin of Thwaites Glacier, and this work contributes to the TIME project of the International Thwaites Glacier Collaboration. Dr. Strickland has a bachelor's degree in physics from Hendrix College and completed his PhD at the Department of Geosciences at the University of Arkansas in Fayetteville. He enjoys teaching and communicating science with the public. Recently, his work was featured in National Geographic, phys.org, and the Copper River Record. The topic of his talk today is internal meltwater drainage, preconditions, debris-covered glaciers for rapid retreat. So welcome, Ryan.
Thank you, Patrick, and I will share my screen. Okay, and hopefully get everything going. Are we able to see the screen well?
Yes, looks great.
Okay, great. Well, thank you for the introduction, and I'm happy to be speaking to all of you today. As Patrick had said, I am now working on Thwaites Glacier and Antarctica, and part of this has been part of that work has required me to learn Elmer ice, and that process has been a little slower than I had hoped. So instead of presenting on my current work, which is on Thwaites Glacier, I'm going to show you some work that I'm still finishing up from my PhD, which I just finished about 6 months ago. And so this work is also quite fresh. Some of it has not been published yet, and it's something I'm also excited about. So I'll get started. And today we're going to focus on debris-covered glaciers. And in case you're not aware, debris-covered glaciers are common in high-relief mountain ranges like we have in the Himalaya, and also in the Alaska range and other parts of the world where there are steep mountains and tectonically active areas. So in these steep mountain ranges, you get very steep glaciers whose accumulation zones are fed by avalanches and rockfall, and all this rock and sediment gets incorporated within the ice in the accumulation zone. And as the glacier flows down the mountain, this debris works its way onto the surface. And as it makes its way to the surface, it directly influences how these glaciers melt. And we can see this quite well in this photo here. You see the ice fall of the Tuscaloosa Glacier in Alaska. And as the glacier flows down, you can see that it's become completely debris covered. But virtually all of this image is glacier. There's glacier ice, flowing glacier ice underneath all of this debris. So the presence of debris directly influences melt. When that debris is really thin, thinner than a few centimeters, the decreased albedo of the sediment increases the melt rate of the ice compared to debris-free ice. But when that debris gets thicker than a few centimeters, the debris actually insulates the ice from melt and slows the glacier from melting. So we've got this sort of competing process going on here. We've got thin debris that accelerates melt and thick debris that slows melt down. So this is up high on a debris covered glacier. As we move down glacier, we start to develop this really high relief terrain that has ice cliffs that we can see here, these bare, thinly debris covered regions that we call ice cliffs. We see ponds as well that form on the surface of the glacier. And there's also in this image, you can see buried stream channels and all sorts of things. So in just the span of a few kilometers from the upper glacier region to closer to the terminus, we go from this really gentle sort of terrain to this very high relief terrain with lots of ice cliffs. And then when you move further down, many debris covered glaciers develop these large complexes of lakes that are connected to one another and eventually can cover the entire ablation area of some glaciers. And these become really important. The presence of lakes greatly enhances melt rates on debris covered glaciers. And this sort of work has been focused on a lot over the last 20 years. But the gist of it is that once you get these large lakes that develop near the terminus of debris covered glaciers, the melt rates of these glaciers goes way up. And in addition, these lakes grow large enough that they can sometimes, due to an ice fall or an avalanche, they can overtop their moraine dam and cause catastrophic floods that destroy entire villages and lots of infrastructure downstream. So, a guiding question that we need to understand for debris covered glaciers in the high mountain world is how fast are these debris covered glaciers going to melt? Because this influences the need there. This affects people downstream who need the meltwater for farming and for generating electricity. But we're also interested in which glaciers are going to be developing these ponds and that will grow into lakes because these lakes greatly increase the rate that the glaciers melt. So some basic physics here. Simple models of debris covered glaciers show that they respond more slowly to a warming climate than a clean ice glacier. And this has to do with what I had mentioned before. This thick debris on the glacier surface decreases the melt of the glacier. So if we have a warming climate, that debris actually slows the rate that our debris covered glacier is going to respond to that warming climate from, something like 50 years for a clean ice glacier to hundreds of years for a debris covered glacier. But lakes sort of complicate this pattern. So we don't actually know how quickly these debris covered glaciers are going to melt in the coming decades. Some more facts about these debris covered glaciers that are going to come in is I'm sure most of us, if we're in the glacier world, in some way or another, are familiar with equilibrium line altitudes. This is the elevation on a glacier where above which you get more snow accumulation and below which you get more melt. For a clean ice glacier, typically you have 60% of your glacier area above this ELA. But for debris covered glaciers, that percentage changes because, again, the debris insulates the ice. And also because of the way the debris cover influences melt, you tend to create glaciers that are less steep in their ablation areas, so they're quite shallow. As you approach the terminus, they become almost flat. And then as the ELA rises, this debris that's within the ice starts to emerge at a higher and higher elevation, and this decreases the gradient even further on the lower portion of the glacier below the ELA, and they get this hummocky topography that develops. And that's going to be the focus of my talk here, is how this hummocky topography develops. So here's another shot of that hummocky topography and this evolution of debris covered glaciers here. So when we have a healthy glacier in balance with its climate, we tend to maintain a thin debris layer near the terminus of the glacier. But as the ELA rises, you sort of get this lower slope surface that starts to develop ponds, and then these ponds can merge into lakes. And what's particularly interesting is that a lot of these glaciers, this development from ponds to lakes can be quite sudden and occur over a decade or two. One of the most well-studied glaciers is or one of the most well-studied ponds and lake complexes is on the Imja Glacier, which is in the Himalaya near Mount Everest. And um, what occurred on this glacier and has occurred on many other glaciers in the region is that these ponds started to develop and then they rapidly merged into this large lake that continues to grow to this day. So what I'm going to be interested in is looking at how this process gets set up. How do we go from a pond-free surface to this huge lake-covered surface? So to summarize that, what processes drive pond and lake development? That is my guiding question here. And the purpose is to understand where, why, and how fast these superglacial ponds develop so that we can better predict melt rates and drainage rates on debris-covered glaciers. And the approach that I'm going to take to do this is through topographic analysis and landscape evolution modeling, which some of you may be familiar with in the geomorphology world, but I'm going to apply it to a glacier surface. So we're interested in the surface processes that are controlling the changes on debris-covered glaciers. And the most important processes that we are aware of on debris-covered glaciers are differential melt, hill slope debris transport, and channel incision from meltwater. So differential melt occurs when we have contrasts in debris thickness. So if we have a region of thick debris adjacent to a region of thin debris, that thinly covered area will melt more quickly, so its surface will go lower, and the thicker covered region will melt more slowly, so you start to develop topographic relief due to differences in debris thickness. Then, as that topographic relief develops, hill slope debris transport takes over. So debris wants to move downhill. And so these thickly covered high regions start to lose all their debris to the more thinly covered low-lying regions. And so you get this sort of oscillation between high and low topography and debris thickness. And then there's channel incision. So as meltwater is generated on the surface, you can create rivers and streams on the glacier surface, and these incise the glacier ice and also create relief. So what we're going to see today are three projects that I've looked at to better understand how relief develops on debris-covered glaciers and how topographic depressions develop on debris-covered glaciers that can form ponds. And so the first one, we're going to look at differential melt, this contrast in debris thickness, by examining the formation of dirt cones. And the second, we're going to look at topographic depressions on debris-covered glaciers, because these are the sort of hollowed out bowl areas in the topography that form into ponds. And then finally, we're going to look at a model that I developed to examine the growth of topographic depressions to see how they may develop into ponds. So, glacier dirt cones. I became familiar with glacier dirt cones during field work that I did in Alaska on the Tusculana Glacier. And while there, I was the purpose of this trip was to look at topographic depressions and ponds and map them and better understand the processes forming them. But along the way, we found these really curious features that I later learned were called dirt cones, and these are meter scale, anywhere from less than a meter to 5 or 6 meters was the tallest that we saw. And these are cones of ice that are covered with a thin layer of debris, and they're really striking when you see them. And hopefully, this image of my PhD supervisor next to one of these dirt cones sort of captures how unique these features look on the landscape. So these are really cool, and I decided to better understand how these features formed while we were there, in addition to the other work I did. So we mapped a number of these features, and we observed that most of these dirt cones were located in this shear margin along the Tusculana Glacier, where there were a lot of crevasses and moulins. And there was definitely a spatial correlation that we observed between the presence of crevasses and moulins and the development of these dirt cones that we saw. And you can see a couple more examples of these dirt cones. And while in the field, we became increasingly convinced that these dirt cones were actually originated as moulins. So if you have a superglacial stream flowing on the surface, it plunges into a crevasse and forms a moulin. And if this moulin fills with debris, the ice at the base of that moulin will melt more slowly than the ice on the surface of the glacier, and eventually you can get this cone is what we hypothesized. And I think these two images that you see here really capture that for me. Um, in the lower inset image, we see this incised channel leading into a deep moulin, and then in the image of the dirt cone, we see sort of a raised ridge leading to a very large dirt cone. And the sediment on this dirt cone is quite weathered from what we hypothesized to be fluvial processes. So we form this conceptual model of how these dirt cones form. So you have water and sediment that flows into a moulin. And then eventually that moulin, due to glacier advection and changes in surface hydrology, gets abandoned, and whatever sediment is deposited at the base of this moulin eventually makes its way to the surface as the surface of the glacier melts. And once that occurs, you get this topographic inversion where it melts more slowly where the debris is than in the surrounding area. So I built a numerical model to simulate this. And in this model, it incorporates subdebris melt. So as debris gets thicker, our ice melts more slowly. And here we're using a hyperbolic model, which has been used in a variety of settings in Alaska and also in the Himalaya for other sort of debris covered glacier models. So it's quite easy to work with. And then we simulate hill slope debris transport using a nonlinear depth-dependent diffusion. So pretty simple model. We just have subdebris melt and hill slope debris transport. And so what I did is we start with a pit of debris and we let the model run. And you can see in this animation and in the snapshot transects on the right that within about a month, we get a substantial dirt cone from a debris-filled pit. So that was cool. This is really satisfying for me because this was an early part of my PhD, and I'd set out to model something and I had succeeded. But we can also learn some things from how these dirt cones develop that help us understand how topographic relief develops on debris-covered glaciers. So when we look a little bit closer at how these develop, and I'm just showing you a single simulation here, but we varied the parameters quite a lot. And what we observed is that the faster debris was allowed to leave the pit, the shorter our cones grew. And through some non-dimensionalization of our model, I derived a length scale that predicts topographic relief from differential melt. And this length scale is just the ratio of our debris diffusion rate, which is analogous to any debris diffusion rate you would use in a landscape evolution model. Usually we use the big letter D for that, or K. And then the ratio of that and the melt rate. So the bigger L is, the bigger this length scale, the less topographic relief we get. And consequently, the shorter this length scale is, the greater the cone, the greater topographic relief we get. So what this means is if we increase the melt rate, we get greater topographic relief, or we get bigger cones in my examples here. But what's has been observed on debris covered glaciers in the Everest region is that over the last 2 decades, they have undergone a large increase in topographic relief in the ablation zones, and it was hypothesized that increased melt was causing that. And now with this simple model that I've created, we have we've sort of quantified this relationship, and we can predict how much relief might increase for any given increase in melt rate. So to conclude this little part of the talk, with this model, we showed the differential melt can produce meter scale dirt cones in a few weeks. And so that's interesting in itself, but maybe the most important finding from this is that the ratio of debris diffusivity and the melt rate controls topographic relief. So we can look at, we can start to predict how topography might change due to changes in melt rate that we observe on the glacier. So now let's turn our attention to the depressions. And these topographic depressions are low spots in the topography, or sinks, topographic sinks, where ponds can form. And when we look at debris covered glaciers, like in this particular example that I'm going to show you as soon as my slide advances, there we go. When we look at debris covered glaciers, and this is the Gazumpa Glacier, we see that the surfaces are covered with thousands of topographic depressions. Each of these sort of red polygons you see on the right panel is an individual topographic depression identified in a DEM that I created due to some photogrammetry while in Nepal. And so the surfaces of debris covered glaciers have thousands of these depressions, but what's kind of interesting is that fewer than 5% actually have ponds. So most of the depressions are dry, which is unusual because ice is essentially impermeable to water. So if we have a topographic depression in the glacier surface, it should fill with water because meltwater from the surrounding area would travel into it. But that's not what we see. And the ponds that actually fill the depressions, the depressions that have ponds, the pond area is typically much, much smaller than the depression area. So both of these are kind of, this is an interesting observation to make because, like I said before, ice is impermeable to meltwater, so we should expect most, if not all, of these depressions to have ponds. And then we should also expect the depressions to be essentially filled with meltwater. And then as they fill, you know, they would essentially encompass the entire depression area, but that's not what we see. So if the depressions are just caused by bare patches or thin patches of debris surrounded by more thick debris, we could create a depression, but it should fill with water, and then debris from the surrounding area should eventually fill that depression, which would slow its melt and eventually lead to the pond to overflow. But this doesn't appear to be what we see. When we look at the depressions, when we look at their areas, the distribution of depression areas follows a power law. And that's what the top panel shows you here. Power law distributions are unique in that they tend to arise only in the absence of negative feedbacks. And so, as I had mentioned a minute ago, debris falling into the depression should slow its growth and be a negative feedback on depression growth. But this distribution suggests that the depressions don't have any negative feedbacks. We also see that our depressions have fractal perimeters, which is often a characteristic that arises from positive feedback growth. So these have a fractal geometry to them. And then our depth area scaling relationship shown at the bottom shows that as our depressions grow in area, they're getting deeper. And again, if our depressions are filling with debris, they should not be getting deeper as they grow. They should, in fact, be getting less deep and eventually undergoing topographic inversion as the depression itself fills with debris and the surrounding area melts. So this is quite surprising to us. We expected to see a characteristic size of depressions, but instead we see that they appear to undergo positive feedback growth. So to better understand that, I built a simple geometric model to see if positive feedback growth could produce distributions similar to the ones that we see on the debris covered glaciers. So what this model does is I begin with really a simple space. It's a square model space, and I populate it with a bunch of circles that represent small depressions. And all of these depressions at the beginning, or all of these circles, were taken from a normal distribution, and to that, we apply a growth rate to these depressions. And that growth rate, we make it proportional to the depression area raised to a power. And so we tried a variety of powers here where R equals 1, this orange line here would represent like exponential growth of these depressions. R equals 0.5 would mean that they grow at a constant radial growth. And these R values that are greater than 1 are what is known as hyperbolic growth, which is what we're really interested in, this positive feedback rapid growth. So we ran a variety of simulations that allowed these circles to either merge and that to influence their growth rate, or they remained individual entities. And what we found on the slide that seems to be missing something, but that's okay, is that we could create positive feedback, or we could create depressions with power law size distributions only when we had hyperbolic growth. So these R exponents that are greater than 1, which you can see with the green dotted line and the yellow line. These are the only two exponents in our growth rate equation that would produce positive feedback, or that would produce power law size distributions similar to what we saw on the Gazumba Glacier. Exponential growth was not enough, and that constant radial growth was also not enough to produce power law distributions. So we really needed this hyperbolic growth where the growth rate of these depressions essentially takes off as the area increases. And another surprising finding from this simple model is that mergers between the individual depressions really didn't influence the outcome of the distributions. So it doesn't appear to matter whether we have a model space that's populated with a bunch of depressions or just a few depressions. We will get power law size distributions solely based on the growth rate exponent. It doesn't require mergers between depressions to do so. So from this, we formed a hypothesis. And so the hypothesis is that we can get positive feedback depression growth if we're able to remove debris and meltwater from the depressions as they grow. And so there's some evidence to support this. Debris covered glaciers have caves within them. We know that many of these depressions drain in glacially through caves. This has been documented for at least the last 20 years, if not more. But what we're really examining here is that I'm arguing that these depressions are the result of in-glacial drainage. And we believe, or at least I believe with these observations, that this is the way that we're going to get positive feedback growth, is by removing the debris. And that's because the debris deposition into the depressions is a negative feedback on growth, and we don't appear to see a negative feedback in the size distributions. And with the debris removal, we can actually get positive feedback growth. But this is just a hypothesis, and it's interesting. It might be compelling, but it still needed a little bit more work to really move forward. So I took that model that I showed you of the dirt cones and I extended it to include superglacial meltwater drainage and also internal drainage of water at sink points. So in this model, I sort of conceptualize uh, a depression forming around a sink point. So where water from the glacier surface can enter an inglacial drainage system. And then I can selectively allow whether or not debris also goes into this sink point and leaves the model space. And from this, I wanted to see, first off, does inglacial drainage or does this internal drainage produce topographic depressions? And then can we get positive feedback growth from this model, similar to what we observed on the Gazumpa Glacier? So our models at this stage are quite simple. We start um, again with a square two-dimensional model space, and at the center of this model space I place a drainage point, and this is where water and or debris can leave the model space. Um, the entire surface is sloped downwards. I chose a 1 degree slope surface because this is comparable to the slopes of debris covered glaciers in the Himalaya and in Alaska, so it was more um, it was similar to what we see in the field. And I covered this surface uniformly with debris. When the simulations start running, as the ice surface melts, uh, drainage channels start to form. If those drainage channels connect with the downslope boundary of the model, that water just leaves the model space at the bottom. And we can think of that bottom edge as maybe being the edge of our glacier, um, where water then enters a more terrestrial environment. But if one of these drainage channels happens to hit the internal drainage point, that water and debris that hits that point can also leave the model space. So we see if depressions can grow. The math, I won't spend too much time on this, but it's really the same model that we saw before, but instead we added a channel incision component that uses a stream power incision, which is similar to what you might see in a terrestrial landscape evolution model. And so we allow drainage channels to erode the ice surface. And then we also allow debris to be removed at the drainage point. As well. So, and we scale that with the drainage area at that point, which is borrowed from the karst hydrology world, where sinkholes are common, and debris removal at sinkholes is common. Also, to help with the model stability here, I added the melt out of inglacial debris. So I have some percentage of debris. In this case, it's about 0.1% of the ice is debris. So as the ice surface melts, a little bit of debris gets added to the surface. And what this does is this just eliminates there being completely barren areas of debris, which cause instability on the surface. But so let's see how this runs. Here's a sort of a 3D view with some rainbow colors here. But at the center, we have a sink point that is allowing meltwater and debris to be removed as the model runs. And so what I hope you can see here is that after about 50 years of simulation time, which this simulation shows, we get a depression that grows and fills virtually the entire model space here. So it seems promising. Internal meltwater drainage and debris removal will produce depressions. So I tried a few things with this model. First, I wanted to see how important debris removal was. So what I could do is I could basically turn off whether or not debris is allowed to be removed at these drainage points. So when there's no debris removal or very little debris removal at the drainage points, only water leaves at the drainage point. And when that removal rate constant is higher, both water and debris can be removed. And what I found is that when you turn off debris removal, or even if you just turn it down quite a bit, you will not get a depression at all. So you absolutely have to have debris removal at these drainage points in order to get topographic depressions to grow there. And that's what this complex of figures is showing here. The top row uh, is a simulation with no debris or very, very slow debris removal at the sink point. And then the bottom row here simulates a higher rate of debris removal at the sink point. And what we can see is that the depression grows larger when we allow debris removal at that sink point. And these figures on the right um, look at the different parameters related to these sink points. So we have the drainage area of the sink point, the depression area, the amount of debris that's removed, and then the depth of the depressions. So basically, if we allow debris to be removed, we get a continually increasing drainage area at that sink point. We get a depression area, which is actually the enclosed sort of bowl that would form a pond if there were no drainage. It grows continuously, and the depression continues to deepen as if we allow debris removal at that sink point. I also examine how the incision rate influences depression growth. And so the incision rate, this constant K, it just essentially controls the strength of incision for a given amount of drainage area and surface slope. So the bigger the value of K, the more deeply incised your channels will grow. And as you might expect, if we increase this constant, this channel incision rate constant, we do get bigger depressions. And if we turn it way down, we hardly get a depression to form at all. So this top row here has the lowest value of K that I examined here, and only a very small depression, a few pixels wide, formed in this simulation. But a doubling of that constant causes a depression that grows and rapidly fills the model space. So incision beneath the debris is an important control on depression growth by this method, and debris removal is also important. Okay, so thus far I've just shown that the depressions grow. This model works, so depressions on debris-covered glaciers could form by internal drainage and debris removal. But I haven't shown that any of this is positive feedback growth. So now I'm going to do that. Here in these different plots, I'm showing you parameter sets that produced positive feedback depression growth, similar to what we saw in the Gazumpa Glacier. And what you should take from this is that we could get positive feedback growth to occur for a really wide range of parameters and debris removal rates. We did not need It wasn't required to have the fastest debris removal rates, nor was it required to have the fastest stream power constants to get positive feedback growth. So we can get positive feedback growth from this sort of mechanism, similar to what we see. And it helped us understand how debris removal initiates this positive feedback. So as debris is removed from the depression at the sink point, it allows the depression bottom to melt more quickly. As it melts more quickly, it gets deeper, which allows it to grow and capture more drainage area. And as it captures more drainage area, more debris is transported to the sink point. and this cycle continues. So debris removal, we believe, is an essential component of this positive feedback, and our model illustrates that. So, kind of the conclusion of findings from this aspect of the work is that debris removal was essential for depression growth here, or any meaningful depression growth. And we can get positive feedback depression growth for a wide variety of parameters, as long as we allow this internal drainage. But if we don't let debris removal occur, hill slope debris transport into the depression will limit relief, and it'll eventually lead to topographic inversion, where basically the depression bottom becomes a high point. So from all of this work that I've shown you, I think we have a more clear picture of how topography develops on debris covered glaciers and how ponds can develop. And that's what I've tried to illustrate here in this cartoon. So when we have a healthy glacier in a stable climate, depressions form around internally drained sink points. Patches of thick debris will form topographic highs, and thinner covered areas will form topographic lows, but these regions will oscillate. But the internally drained areas will become depressions that continue to grow. If the climate warms or conditions change around that glacier that cause it to undergo thinning, that surface lowers, and as these depression bottoms reach the hydrological base level, which is set by the outlet elevation of the glacier, these depressions can no longer drain internally, so they become filled with ponds, and these ponds can rapidly merge with one another. And this really meshes nicely with what we observe, where debris covered glaciers can go from having almost no ponds to suddenly having a huge complex of ponds that last from year to year. So I think we've shown that internal drainage is a key part of that, and a key part of understanding the evolution of debris covered glaciers is understanding the evolution of these internal drainage systems. So that is all I have for you guys. I hope you enjoyed the talk, and well, I stopped sharing, but I can reshare again. I just can't see anybody until I stop sharing. So thank you.
Thanks a lot, Ryan. That was quite interesting. Uh, do we have any questions?
Hi, yeah,
Hi.
enjoyed that. Thank you very much. I've worked near the Bering and the Malaspina glaciers in
Hmm.
Alaska, and my question, I came in a little bit late, so maybe I missed this, but I would have thought that covered glaciers would, because they're darker, have a more rapid melt rate.
Hmm.
You said they
Yeah,
don't. Yeah,
they don't. So that's due to basically when the debris gets thicker than a few centimeters, the heat transfer
protecting
through the debris is so slow that it
it.
doesn't it reduces melt compared to bare ice. But on like sort of like a global average is when debris is thinner than about 3 centimeters, the debris cover increases melt compared to bare ice, so the glacier would melt faster. Um, but when the debris
But
gets thicker than that, the insulative effects take over.
okay, so the insulation outweighs the albedo, basically, you're
Yeah,
saying. Yeah.
yeah.
Um,
So like typically high on the glacier where the debris first emerges on the glacier surface, the debris is quite thin. And so what's kind of unique about debris covered glaciers is their sort of melt pattern is different than you would see on a clean ice glacier. You actually get the fastest melt rates really just below the ELA, where the debris is thinnest. And then near the terminus, even though it's much lower elevation, there might be 1 or 2 or 3 meters of debris covering the ice by that point. And so the melt rate is from non-hydrological processes is effectively zero
Hmm.
in
Okay.
that
I
case.
think both of those glaciers, I mean, they're each the size of Rhode Island, and they've changed dramatically in the last 20 years. So, um, might be interesting for you to take a look at them. Yeah.
Yeah, well, I mean, there's in the debris cover world that we have this debris cover paradox, and that's these debris cover glaciers should be melting slower, but they're not really. They're just melting differently. And
Mhm.
so getting a handle on why that has driven a lot of the work in this field over the last 2 decades, to
Hmm.
really pin down like when are we going to have peak melt from debris cover glaciers because Nepal, India, China, Pakistan, all of these countries depend quite a lot on seasonal melt from these glaciers. So yeah,
Okay, thank you.
interesting. Yeah, thank you.
Any other questions? Actually, along those lines, I was wondering sort of how you might integrate this into models of the whole glacier. Um,
Yeah, so unfortunately, this work had to sort of stop when I took my research fellowship here. But the model that I have, it's a gridded model. It would work with any sort of gridded data. So, sort of what would be an ideal for me would be to have a time series, DEM of a debris cover glacier at about 1 meter resolution. And from that, you can basically inversely get an idea of how thick the debris is on the glacier surface. And then I could take that and plug it into the model and start to play around with the parameters. And if you have a long enough time series, I could start to see, well, where's the model doing well and where is it not working at all? Um, and I know this data is out there, but I don't have it right now. So um, hopefully one day I'll be able to collaborate with somebody or get to go back out there and create a good time series. Um, but yeah, it really needs that sort of long-term validation. And unfortunately, I only had the ability to go to the Gazumpa Glacier 1 year in a row. And really, you would probably need at least 3 consecutive years so that you could have a bit to compare to. But
got it.
the
Yeah.
longer the better. You know.
Would you be willing to say a few things about your expected work on the weights?
Yeah, of course. So I can tell you what I'll be talking about at EGU and what I'd hope to talk about today. So I'm part of this big state Thwaites Glacier project, and I just came in on it. And so what I'm working on right now is I have some swath radar data beneath Thwaites that's about 25-meter resolution, so it's quite good. Um, and I'm looking at how these sort of small and medium scale topographic features influence the development of temperate ice at the glacier bed. And so I'm looking at three different sites. One has a large canyon of about 100 meters relief that's oriented perpendicular to flow. And I've got another site that I'm looking at that's got nice long lineated features, so it's much smoother. Um, and I'm forgetting my third site, but basically we're looking at the difference between how flow varies between these sort of long, durable topographic structures that are likely bedrock, like around this canyon where the topographic highs are expected to be quite they're expected to be bedrock, and then in this lower area where we're getting more sediment bed. And so what I'm looking at is again like how these features influence flow, and then um, the development of tempered ice over those locations. More long term, I'm looking at the evolution of the eastern shear margin of Thwaites Glacier. So just to make sure we're on the same page, shear margins are where fast ice is moving adjacent to slower ice near the kind of the periphery of the glacier. So ice streams on Thwaites Glacier and numerous ones flowing into the Ross Shelf and elsewhere in Antarctica and Greenland. You have these ice streams, and so where this fast ice meets the slow ice, you have a shear margin. Most shear margins are essentially located above topographic features at the glacier base that sort of control where the ice is going to flow. But that doesn't appear to be the case for the eastern shear margin. And so it seems that its shear margin position is subject to migration. And if the shear margin were to migrate outwards, the width of Thwaites Glacier's ice stream gets wider and a tremendous amount more ice flows into the sea. But of course, if the margin moves inwards, then then less ice would flow to the sea. So broadly, I'm supposed to look at things that will be controlling the stability of this margin. And so I've got a few ideas there, but I'm still in the sort of foundation phase of learning how to use Elmer and sort of getting some good research questions together. But I'm hopeful to use some new 3D seismic data that they collected a couple of years ago in Antarctica, which hopefully those papers will be coming out soon. But they had a pretty awesome seismic campaign across the shear margin during their last field season. So.
Thanks.
Yeah, thanks. And yeah, hopefully I'll be able to give a talk on that in the next couple of months. But yeah, my model just got working about a week and a half ago, and I'm not ready to talk about the results yet. So.
Okay, we have another question in the chat. Minak says, as the debris drains, it might also enlarge the drainage pathways, right? That could serve as another positive feedback.
Yeah, that's probably true. I think there's a lot of interesting things to look at in relation to sediment transport in streams on glaciers. I think it's pretty well unexplored, at least to my knowledge. There's definitely some work looking at channel incision, but no sediment transport. And so, yeah, the potential for mechanical erosion of the ice surface from tumbling blocks is probably not negligible. Anecdotally, I can say that in a little stream that is no more than 10 or 20 meters deep and a meter or two across, you can toss a block as big as a softball into the water, and it just runs on down. So these superglacial streams can have tremendous sediment transport capacity, at least compared to what you might see in a terrestrial stream, because you essentially have a frictionless surface or almost frictionless surface at the base. And within the caves, I've done a little bit of cave surveys. These caves, I mean, they're definitely transporting sediment. But how much sediment is unknown, and where that sediment really ends up is unknown. Is it being stored at the glacier bed or within the glacier, or is it re-emerging somewhere down glacier? But Yeah, I mean the model I presented definitely introduces a lot of questions that would be worth checking out in the field.
Okay, any other questions? Guess we're at the hour, so we could stop there. Yes.
Yeah. Well, thank you for inviting me, Patrick.
Yes. Thanks
And
again.
Thank you.
yeah, thank you all for attending. And yeah, I hope to talk to you guys about thwaites in a few months.